What if the solar system is far stranger than most people were ever taught to believe, from the planets moving in the same plane, to Jupiter's true nature, to the hidden edge of the sun's influence? Some of the most familiar ideas about our cosmic neighborhood are also some of the most misunderstood. Tonight, this journey goes beyond the textbook version of space and into the deeper mysteries that still leave astronomers searching for answers. Before we begin, please take a moment to like the video, subscribe to the channel, and share it with someone who loves science and cosmic mysteries. And as always, thank you so much for watching and supporting the channel. It truly means a lot. If listening tonight, feel free to leave a comment and share what time it is and where in the world this video is being heard. Now, settle in and let us begin the journey into what most people get wrong about our solar system. The familiar picture of the solar system begins as a flat arrangement, almost like a diagram too simple to be true. The sun sits at the center. Thin paths circle around it. Mercury sweeps close in, then Venus, Earth, Mars, the asteroid belt, the gas giants, and the dark outer frontier beyond Neptune. In that picture, everything seems to belong to one shared surface, as if the planets have been placed on the same invisible sheet. Most people accept that image without much resistance because it appears everywhere, in textbooks, museum displays, animations, and classroom posters. Yet the deeper question remains strangely easy to overlook. Why is the solar system like that at all? Why do the major planets orbit in nearly the same plane? Why do they also travel in the same direction? Why is the arrangement not scattered into every angle, every tilt, every possible path around the sun? At first glance, it almost looks like a design choice. Nature, however, does not usually offer neat geometry without first passing through disorder. In space, where distances are immense and collisions can happen over millions of years instead of moments, it might seem more natural for worlds to approach a star from every direction. A person looking only at the finished arrangement might expect a swarm rather than a disk, a tangled cloud of independent orbits rather than a broad, coordinated wheel. Yet the real solar system refuses that expectation. The planets do not move at random. They are not stacked above and below the sun in some chaotic three-dimensional spray. They stay close to one common plane, with only modest deviations. Mercury is somewhat tilted. Pluto, now classed as a dwarf planet, is far more inclined and eccentric than the 8 major planets. Even so, the main pattern remains obvious. The great bodies of the solar system mostly travel in a shared, disciplined flow. That alone would be interesting. But the pattern does not stop with planets. It repeats. Jupiter, Saturn, Uranus, and Neptune are each surrounded by families of regular moons, and those moons usually orbit close to their planet's equatorial plane and in the same general direction as the planets spin. Saturn's rings, perhaps the most elegant structure in the solar system, wrap themselves around the planet in the same flat style. Thin, bright, and layered. They look fragile from a distance, but they follow the same rule with astonishing loyalty. Around the sun, around the giant planets, again and again. Matter settles into ordered planes and shared motion. It is not a single coincidence. It is a habit of nature. That habit becomes more striking the longer it is examined. A random event can produce a random outcome once. Repetition suggests a process. Planetary systems beyond the solar system appear to support the same idea. Observations from missions such as Kepler, along with measurements made by large ground-based observatories and space telescopes, show that other stars can host families of planets that also move in orderly configurations. Some systems are far stranger than this one, with giant planets packed close to their stars or worlds locked in resonant timing. But even there, the tendency toward disks and aligned motion appears again and again. Around young stars, astronomers have seen broad disks of gas and dust glowing in infrared light, shaped like flattened halos. The European Southern Observatory and the Atacama Large Millimeter Array have revealed rings, gaps, spirals, and dark bands in those disks. They do not look like finished solar systems, but they look like beginnings. They suggest that flatness is not an accident discovered once. It may be the natural footprint of formation itself. Even so, the picture is not perfect, and that imperfection is where the mystery deepens. The solar system is not truly flat. No honest account can claim that. Every planet is tilted at least a little from the mean plane, and some are offset more clearly than others. Uranus spins on its side. Venus rotates in the opposite direction compared with most planets. Many smaller bodies follow eccentric and inclined orbits. Some moons are irregular captures, moving at odd angles and even in reverse. Asteroids and comets arrive from directions that seem to ignore the general order altogether. The system contains obedience, but also rebellion. That combination matters. It suggests that the flatness is not a rigid law imposed from outside. It is more like a dominant memory, strong enough to shape most of the architecture, but not strong enough to erase every later disturbance. That memory may be the most revealing clue of all. In ordinary life, order often suggests control in the present. In astronomy, order often points backward. It hints at a vanished condition that once governed everything more directly than it does now. The present solar system may simply be the cooled and settled remainder of something much more violent. The nearly shared orbital plane could be less like a rule the planets actively follow and more like a scar left by their birth. Seen in that way, flatness becomes evidence. The planets may not be choosing anything. They may merely be continuing a motion given to them long before Earth existed. Long before the sun shone steadily. Long before any surface had fully formed. This is where the familiar classroom image begins to feel misleading. The neat rings imply calm, but the calm comes last. Before the planets move in elegant paths, something else must happen. Matter must gather. It must collide. It must lose some motions and preserve others. That is the hard part to imagine, because space is often pictured as empty and still. In reality, the early environment around a forming star is restless. Dust grains strike one another, gas falls inward, fragments merge, shatter, and merge again. Speeds change, directions cancel, heat rises, gravity deepens. The final order is not the opposite of chaos. It is what survives chaos. There is something unsettling in that idea because it turns a peaceful arrangement into the aftermath of elimination. If a cloud collapses toward a forming sun from many directions, then countless motions are possible at the beginning, yet the finished system preserves only a narrow range of them. Most possible paths disappear. They're cancelled by impact, damped by frictioning gas, or absorbed into the growing mass at the centre. What remains is not every direction matter once tried to take. It is the one direction that wins. The solar system may therefore be flat for the same reason a river eventually chooses one channel through a landscape. Not because other routes never existed, but because repeated interactions remove them. The deeper question, then, is not simply why the planets share a plane. It is why so much matter, from so many possible beginnings, ends up surrendering to one preferred motion. There is a known physical answer waiting in the background, and it involves angular momentum, the conserved tendency of matter in motion to keep a kind of spin. But even before the technical language enters, the basic mystery is already visible. A cloud has no reason to become a clockwork system unless some hidden bias is present from the start. Somewhere in the earliest collapse, amid gas, dust, turbulence, and falling fragments. A slight overall rotation must exist. It may be tiny, it may seem insignificant compared with the disorder around it, yet over time, that weak preference can outlast the noise. It can become the master pattern, and that possibility carries an eerie implication. The modern solar system, for all its worlds and weather and storms and impacts, may still be obeying a faint rotation inherited from a cloud that vanished billions of years ago. The planets may circle where they do because the ancient nebula that made them never fully stops speaking. Its original motion remains buried in every orbit, every ring, every regular moon. What looks like quiet order in the present may actually be a message from a forgotten beginning, still readable only because nothing powerful enough has erased it completely. Long before the planets settle into recognizable paths, before Jupiter swells into a giant and Saturn lifts its rings into view, the solar system exists only as a region inside a much larger darkness. It is not yet a system. It is not even a star with companions. It is part of a cold molecular cloud, one of the immense drifting nurseries where hydrogen, helium, dust, frozen compounds, and trace heavier elements remain suspended in a loose balance. For long stretches of time, nothing dramatic seems to happen there. The cloud is thin beyond ordinary intuition, yet across enormous distances it holds enough mass to make stars. It is quiet only in appearance. Inside it, particles move, pressure pushes outward, gravity pulls inward, magnetic fields thread through the gas, and nearby events can disturb the balance without warning. A stellar nursery is not a peaceful cradle. It is a waiting place filled with delayed consequences. At some point, that balance fails. The trigger may come from a shockwave moving out from a nearby supernova, or from the winds of massive stars, or from collisions between cloud fragments, or even from the slow internal evolution of the cloud itself. The exact cause of the sun's birth is still uncertain, and that uncertainty matters, because it leaves the first step partly hidden. Meteorites preserve hints that material from a dying star may have entered the young solar system shortly before or during its formation. Short-lived radioactive elements found in ancient rocky fragments suggest that something violent and nearby may have helped shape the beginning. That clue does not solve the puzzle completely, but it sharpens the scene. The solar system may not begin in isolation. It may begin because something else dies close enough to disturb the cloud and seed it with fresh material. A star may owe its birth to another star's destruction. Once the inward collapse begins, the transformation is ruthless. Gravity, which had been balanced for ages by outward pressure, starts to gain ground. Gas and dust fall inward. Regions of slightly greater density pull in more matter and become denser still. Clumps form inside clumps. The center of the collapsing region thickens. Temperature rises as gravitational energy is converted into heat. Collisions become more frequent. Dust grains stick together, break apart, then stick again. What looked diffuse and uncommitted begins to organize around one growing core. Yet this does not happen as a perfect plunge from all sides into a point. The collapsing cloud carries history with it. Even a cloud that seems almost motionless can possess a tiny overall rotation. It may be weak enough to go unnoticed at first, but gravity magnifies its consequences. This is where the story becomes less intuitive and more revealing. If matter falls inward from every direction, then pure symmetry would suggest total confusion. But a collapsing cloud is never perfectly symmetrical. There is always some unevenness, some leftover drift, some slight net spin inherited from earlier motions in the cloud. As the cloud shrinks, that spin becomes harder to ignore. The same physical principle that makes a skater spin faster when drawing inward applies on the scale of star formation. A vast, slow, turning region contracts, and the turning intensifies. The growing central mass continues to attract material from many directions, but now those inward paths no longer meet in equal competition. Opposing motions collide and partly cancel each other. Motions that support the overall rotation are preserved. Little by little, chaos is filtered. This filtering process is more severe than the finished solar system suggests. It is not just that matter gathers, matter is sorted. Gas moving against the main flow collides with gas moving with it. Dust grains strike and exchange momentum. Orbits that plunge steeply through the forming structure experience drag in the surrounding gas. Energy is bled away. Some material falls directly into the center. Some is thrown outward. Some settles into flatter and flatter paths. In time, the collapse stops looking like a sphere and starts looking like a disk with a swelling center. The shape is not imposed from outside. It is the inevitable result of many cancelled motions leaving one preferred direction behind. At the heart of that flattening cloud, the protostar begins to emerge. It is not yet a true star in the full sense because hydrogen fusion has not fully ignited in its core, but it is already powerful. It glows from heat generated by infall and compression. Around it, the disk thickens and spreads, far from being a decorative ring. This protoplanetary disk becomes the real workshop of the future system. The Sun does not simply appear first and then receive planets later as if they are added ornaments. Star and disk grow together. The center feeds on the disk responds to the center. They are parts of one evolving structure. The Sun gathers most of the mass, but not all of it. What remains in orbit is the reservoir from which planets, moons, asteroids, and comets will eventually emerge. Modern astronomy has seen glimpses of this stage around other stars, and those glimpses give the old idea weight. Radio observatories and infrared telescopes reveal young stars wrapped in dusty disks, some with striking concentric gaps, some with broad asymmetries, some with twisted spirals that seem too elaborate for such early ages. In some systems, dark lanes appear where matter may already be clumping into unseen worlds. In others, entire regions look carved away, as if something inside the disk is clearing a path before the planet itself can be directly observed. These images do not show the solar system's own birth, but they show that the process is real. They also show that it's not always tidy. Even at the beginning, order grows out of instability rather than replacing it. That instability raises a quieter mystery. If disks are common, and if disks naturally produce planar systems, then why do so many planetary systems still end up so different from one another? Why does one star host hot giant planets pressed close to its surface while another holds compact chains of rocky worlds? Why do some systems appear remarkably flat and calm while others seem disturbed, misaligned, or incomplete? The answer may lie in events that happen during and after formation, but the question points back to the beginning. A disk provides a memory of one main direction, not a guarantee of one final design. The solar system may look orderly now, but its order may be only the surviving fraction of a much more unstable past. There is also the matter of time. Human intuition imagines collapse as sudden, almost like an explosion played backward. In reality, the forming system evolves across long spans. The first dense concentration grows over thousands of years. The protostar continues accreting. The disk persists for millions of years, changing as radiation, magnetic turbulence, shock fronts, and collisions reshape it. During that interval, the solar system is neither finished nor secure. It remains vulnerable to outside influences from nearby stars in the natal cluster, to internal turbulence that stirs the gas, and to violent mergers between growing bodies. The flat arrangement that later seemed so natural is still being negotiated. It is not born perfect. It is hammered into persistence. And through all of it, one fact remains strangely powerful. The planets that exist billions of years later still carry the geometry of that hidden collapse. Their orbits preserve the faint signature of a cloud that no longer exists. The early solar system is not remembered by photographs or direct records. It is remembered by motion. Every world circling the sun close to the same plane testifies that the ancient cloud does not collapse in total confusion. It chooses a direction, or rather reveals the one direction it has possessed all along. Too weak to matter at first, too stubborn to disappear in the end. The disk has not yet made the planets, but it has already decided the stage on which they will be allowed to appear. The disk does more than hold material in orbit. It remembers. That is the strange part. It forms out of collisions, losses, cancellations, and falling debris. Yet instead of becoming more confused with time, it begins to express one dominant rule with increasing clarity. Almost everything that will later define the broad architecture of the solar system is already being written into this spinning structure while the sun is still young and unstable. The planets do not yet exist as finished worlds. Their surfaces are not formed, their atmospheres are not settled, their moons are not assembled, and yet the disk has already imposed the most important condition of all. It has chosen the plane in which most of that future must unfold. What appears later as neat celestial choreography is, at this stage, still only a stubborn preference inside a cloud of dust and gas. But it is enough. The physical reason is well known, though its consequences remain quietly dramatic. Angular momentum, once present, resists being erased. That term can sound technical, but in plain language it means that matter already moving around a center tends to keep moving around that center unless something forces a change. In the early solar system, many forces do exactly that. Gas drags on dust. Dust collides with dust. Larger clumps begin to stir the material around them. Some trajectories are steep, some are retrograde, moving against the growing overall flow. Some plunge inward too fast. Those conflicting motions do not survive equally. They grind against the denser disk, lose energy, and either fall toward the protostar or settle closer to the shared plane. The disk behaves almost like a filter that keeps rotation but removes disobedience. It does not need intelligence to do this. Repetition is enough. Billions upon billions of collisions, each too small to notice alone. Create a structure that seems planned only because the alternatives have been worn away. This is one of the reasons the early solar system is so hard to picture honestly. Ordinary imagination expects disorder to become more disorderly, yet under gravity, with enough matter and time, repeated interactions can produce something more selective. The disk is still chaotic in many local ways. Shocks pass through it. Turbulence ripples across it. Temperature changes from the hot inner region to the cold outer distances. Charged particles interact with magnetic fields. Streams of gas drift inward while other material is pushed outward. Some models suggest that turbulence produced by magnetic effects helps move angular momentum through the disk, allowing gas to spiral into the young sun while other parts spread farther out. This means the disk is not a still record. It is an active machine, constantly rearranging itself while somehow preserving its overall memory. That combination is the source of its power. It changes continuously, but its main direction remains. Evidence from elsewhere gives this hidden stage unusual credibility. The Atacama Large Millimeter Array has shown young stars surrounded by disks so sharply structured that they no longer resemble vague clouds. One of the most famous examples, the young star often called H.L. Tauri, appears within a disk marked by bright rings and dark gaps. The image is not a direct photograph in the ordinary sense, but a reconstruction from radio observations, and yet the message is unmistakable. Nature builds order early. Another system, PDS 70, offers something even more startling. Astronomers have found direct evidence of forming planets still embedded in the disk itself, carving out lanes as they gather material. Around at least one of those growing planets, observations suggest the presence of a smaller surrounding disk from which moons may one day emerge. In that one scene, the larger pattern repeats inside the smaller one, a star with a disk, a planet inside the disk. A moon-forming disk around the planet, flatness within flatness, memory nested inside memory. This repeating geometry begins to feel less like one local event and more like a preferred method used by gravity whenever enough matter, motion, and time are available. The solar system is not exceptional because it forms a disk. It may be ordinary in that respect. What makes it compelling is that the evidence of its earliest disk survives so clearly after billions of years. Even the Sun's rotation still points roughly in the same broad direction as the planetary orbits. Not perfectly, but close enough to suggest a common origin. The planets spin in ways that are more complicated, partly because later impacts alter them, but the fundamental alignment remains visible. The system still leans in the direction chosen when the cloud collapsed. Yet this is where a more unsettling thought appears. If the disk preserves one preference so effectively, then even a tiny imbalance at the beginning can shape the fate of everything that follows. The planets may owe their arrangement to a slight original spin so small that, in the earliest cloud, it would have seemed insignificant compared with the surrounding disorder. That is a difficult idea to resist dwelling on. Entire worlds, climates, oceans, magnetic fields, and the conditions for life may all depend, at least indirectly, on a near-invisible asymmetry present before the Sun existed. The solar system may not be the product of a grand design so much as the amplified consequence of a small initial bias that refuses to vanish. And there is no guarantee that the process is smooth. In fact, many clues suggest otherwise. Meteorites, especially the oldest known inclusions preserved within primitive chondrites, indicate that solid grains condense, heat, melt, and cool in episodes that are anything but serene. The inner disk appears to undergo violent bursts of energy. Short-lived heating events may flash through dusty regions. Material may be transported outward and inward repeatedly. Some ancient grains found in meteorites are older than the Sun itself, survivors from earlier stars that become mixed into the forming disk. That means the solar system's memory is layered. It remembers not only its own collapse but also fragments of an older galactic past carried into the cloud before the Sun forms. The disk is therefore not a clean beginning. It is a place where inherited debris, new motion, and active destruction all mingle. As the disk evolves, dust grains begin sticking into larger aggregates. At first the process sounds easy. Tiny particles touch and cling through electrostatic effects, forming porous clusters. But growth soon runs into problems. Collisions can become too violent, shattering aggregates instead of enlarging them. Particles can drift inward toward the Sun before they have time to grow much larger. This is one of the early barriers in planet formation. The system seems ready to make worlds, yet simple accumulation can stall. To overcome that barrier, local concentrations of pebbles and dust may become dense enough for gravity to take over more suddenly, collapsing clusters into larger bodies called planetesimals. These are not yet planets, but they are large enough to begin changing the rules. They can attract matter more efficiently. They can stir nearby debris. They can collide catastrophically. Once they exist in significant numbers, the disk becomes a battlefield of construction and demolition. Still, even this violence respects the disker's memory. The planetesimals grow and collide mostly within the shared plane. Their orbits may become eccentric, their inclinations may increase. Some are scattered outward, some fall inward. Yet the overall system does not dissolve into a sphere because the gas is still present for much of this time, damping extremes and pulling matter back toward flatter motion. The disk remains the governing environment. It is not merely the place where planets appear. It is the force that teaches them how to move before they are fully themselves. A modern observer might assume that the solar system is stable because it has had so long to settle, but the deeper truth may be the reverse. It is stable now because it passes through a period when instability is managed by the disk. Once the gas is gone, many of the old restraints vanish. Gravitational scattering becomes harsher. Resonances can shift worlds from one region to another. Giant planets can migrate. Small bodies can be ejected. Late impacts can reshape spin axes and strip atmospheres. In other words, the disk is the last great ordering influence before the system begins testing its own boundaries. That is why its memory matters so much. It provides the common stage before later chaos starts editing the cast. Seen this way, the near-planar arrangement of the planets is not a trivial fact of astronomy. It is a surviving signal from a specific phase in cosmic history, one that lasts only a few million years but governs billions that follow. This solar system may spend the vast majority of its existence without a disk, yet the disk leaves a mark so deep that the planets never fully escape it. Even the exceptions prove the rule. Tilted worlds, captured moons, eccentric dwarf planets, and long-period comets stand out precisely because the background order is so strong. They are disturbances against a remembered field. The disk remembers because physics allows some patterns to survive selection better than others. But to anyone looking at the finished solar system, that explanation does not make the result less mysterious. It makes it stranger. Order here is not the opposite of violence. It is the residue of violence. The planets move in roughly one plane because other possibilities are crushed, damped, or consumed. The disk does not gently arrange them. It permits only the motions that can endure inside its grip. And when the disk is gone, the worlds it leaves behind continue tracing its forgotten geometry, as if a vanished structure still surrounds them, still guiding them, still whispering the direction in which the whole story first begins to turn. Once the disk has imposed its broad rule, matter begins trying to become something more permanent. The solar system is still young, still crowded, still full of collisions, but now the chaos changes character. It is no longer just dust and gas responding to a growing sun. It becomes a contest between emerging bodies, each one large enough to influence its surroundings, small at first, then steadily less small. Pebbles gather into planetesimals. Planetesimals collide into protoplanets. Some of those collisions are gentle enough to build, some are violent enough to erase what was already formed, and yet, through all of this, a pattern keeps returning. Worlds are not born in isolation. They emerge from debris fields shaped by the same flattened memory that shapes the larger system. The disk around the sun gives rise to planets, and around some of those planets, smaller disks begin the same work again. This repetition is one of the strangest quiet truths in planetary formation. A process that first seems unique to stars turns out to be scalable. The sun forms inside a collapsing cloud and gathers a disk. In that disk, giant planets begin to take shape, especially beyond the warmer inner regions where ices can survive and add mass more quickly. Around those giant planets, if enough material collects and remains bound, a circumplanetary disk can form, smaller than the disk around the sun but governed by a similar logic. Gas, ice, and dust circle the planet. Collisions damp erratic motions, material flattens, clumps emerge. Moons may be assembled there in the same way planets are assembled around a star. The architecture repeats, not exactly, but recognizably. Gravity seems to prefer nested systems. The regular moons of the giant planets preserve this history as clearly as the planets preserve the memory of the solar disk. Jupiter's large moons orbit close to its equatorial plane and mostly in the same direction as Jupiter's spin. Saturn's major moons do the same. So do the large regular satellites of Uranus and Neptune, with the important caution that Neptune's moon system bears scars of later disruption. These regular moons are different from the irregular moons, which often travel on distant, tilted, eccentric, and sometimes backward orbits. The difference matters. Regular moons look borne in place. Irregular moons look captured, intercepted, or violently rearranged. The solar system keeps both records at once. One speaks of orderly local formation inside a disk. The other speaks of intrusion and disturbance. Saturn offers perhaps the clearest visible reminder that world-building never fully becomes a thing of the past. Its rings appear serene from a distance, pale bands wrapping around the planet in almost impossible symmetry. But close up they are restless. The Cassini mission, which spends years exploring the Saturn system, reveals that the rings are not solid sheets. They are swarms of ice-rich particles, from dust-sized grains to blocks large enough to cast shadows and open gaps. Ringlets braid and ripple. Waves travel through them under the pull of nearby moons. Small bodies shape edges and carve narrow divisions. In places, Cassini observes clumps and temporary features that suggest material gathering, then dispersing, then gathering again. Tiny moonlets appear to form and fade inside the rings. Some survive only briefly, some persist. It is an echo of the ancient solar system in miniature, a reduced and ongoing version of a much older story. That does not mean Saturn's rings are simply a young solar disk copied at smaller scale. The environment is different. The ring particles move under the planet's powerful tidal forces. Material too close to Saturn can be pulled apart instead of assembled into a larger moon. There is a limit, often described through the idea of a tidal boundary, within which gravity from the central body can prevent loose material from consolidating. That is one reason rings can exist at all. Yet the boundary is not absolute in every detail, and local clumping still occurs. The rings are therefore suspended between making and unmaking. They are orderly but unstable, beautiful but temporary. They suggest that the solar system may never fully stop attempting to build worlds, even in regions where those attempts are repeatedly frustrated. This tension between growth and destruction runs through all early planetary history. Earth itself likely forms through a long sequence of mergers between protoplanets. The same is true for the other rocky worlds. The final stages are not neat accumulation but catastrophic impact. One of those impacts, according to the leading model for the Moon's origin, involves a Mars-sized body striking the young Earth and throwing enormous amounts of material into orbit. That debris later gathers into the Moon. If that picture is broadly correct, then even one of the most familiar objects in the sky is born from wreckage. The Moon would not simply be a leftover companion. It would be the reorganized aftermath of a collision violent enough to melt rock, reshape Earth's outer layers, and fill near Earth space with orbiting debris. A stable satellite would emerge from one of the most extreme forms of disorder the young solar system can produce. The same possibility appears elsewhere. Pluto and its large moon Charon may also be the result of a giant impact in the distant outer system. Some moons may be captured objects, but others bear signs of forming from local debris. In that sense, debris is not a sign of failure in planetary history. It is one of its essential raw materials. The solar system builds by breaking. Each collision that destroys one arrangement also creates the conditions for another. Sometimes the result is a moon, sometimes a ring, sometimes a family of fragments, sometimes nothing durable at all. The distinction is not always obvious in the moment. A cloud of shattered ice orbiting Saturn can look temporary and still hold the seeds of future structure. A giant impact can look like a terminal catastrophe and still produce a lasting companion. This makes the regularity of planetary systems more surprising, not less. There is no shortage of violence that could have erased the shared pattern entirely. Giant planets form and may migrate through the disk. Resonances shift. Smaller bodies are scattered inward and outward. Simulations of early solar system evolution often show that planets can move far from where they begin, exchanging angular momentum with gas or with swarms of planetesimals. Some models suggest that the giant planets, especially Jupiter and Saturn, may alter each other's migration and help sculpt the final layout of the outer system. Neptune may move outward, disturbing icy bodies and helping populate the scattered regions beyond it. If all of this happens, then the solar system does not merely form and cool, it rearranges itself while still young, and yet even with migration, scattering, and impact, the common plane persists. The memory of the disk proves stronger than many later disturbances. At the same time, not every object remains loyal to that memory. The irregular moons are reminders that not all companions are native. Around Jupiter, Saturn, Uranus, and Neptune, distant captured moons travel on inclined and often retrograde paths, almost like invaders that enter after the main architecture is in place. Their existence reveals that the gravitational environment of a giant planet remains open to surprise. Some bodies do not form in the local disk. They are stolen. Others may be fragments from broken captures or collisions among earlier moons. Neptune's great moon. Triton stands out most sharply. It moves backward compared with Neptune's rotation, and likely begins as a captured Kuiper belt object. Its capture may disrupt any earlier regular moon system Neptune possesses, causing collisions, losses, and reassembly. One event can rewrite an entire local history. Even nested systems are vulnerable. That vulnerability adds a deeper layer to the pattern. The solar system is not a sequence of perfect disks producing perfect families of worlds. It is a sequence of temporary ordering episodes repeatedly interrupted by later events. A disk creates the first stage. Growth fills that stage with bodies. Collisions alter them. Captures invade them. Tides pull them apart. New debris appears. New structures emerge. The system is orderly only in the broadest sense. At close range, every world carries scars. Mars may preserve the memory of lost water and ancient bombardment. Mercury bears a giant iron core that hints at unusual early stripping or differentiation. Uranus may have been knocked into its severe tilt by colossal impact or by a sequence of smaller ones. Venus turns backward, perhaps because of atmospheric tides, impacts, or both. Even the apparently clean plane of the solar system is built from objects whose local stories are full of disruption, and yet the repeating geometry refuses to disappear. Around the Sun, worlds circle in one broad sheet. Around the giant planets, the regular moons do the same. Around Saturn, rings flatten into brilliance. Around young exoplanets in distant systems. Astronomers now suspect smaller disks may be feeding the birth of moons beyond this solar system as well. The pattern appears wherever matter is given enough time to collide, enough freedom to orbit, and enough gravity to remember. It begins to feel less like a coincidence of local history and more like a deep preference written into how structure emerges from motion. Still, that raises the question the solar system never fully answers. If matter naturally falls into such repeating order, why do the final results remain so uneven, so scarred, so partially unfinished? Why do some disks produce grand satellite systems, while others yield shattered fragments or captures on backward paths. Why do rings survive around one world while another world holds only scattered remains? The answer may be that order in space is rarely absolute. It is provisional. It lasts until something stronger interferes. The solar system is full of things that form because a disk makes them possible, and full of things that survive only because later chaos does not quite manage to erase them. Each planet, moon, and ring is therefore more than a finished object. It is a compromise between memory and interruption, between the calm geometry of a disk and the endless accidents that follow. The worlds are born from debris, but the deeper mystery is that debris ever learns how to organize itself at all. Jupiter enters the story as a temptation. It is so large, so dominant among the planets, so swollen with hydrogen and helium, that it invites the same question generation after generation. Could it have been something else? Could it have crossed the line between planet and star? Could the solar system once have held the possibility of a second sun? Dimmer, perhaps, but still radiant enough to change every world around it. The idea survives because Jupiter already feels like an exception. It contains more mass than all the other planets combined. Its magnetic field is enormous. Its storms outlast centuries. Its retinue of moons resembles a miniature system in its own right. Seen from a distance, it looks less like a planet that happens to be large and more like a body that almost belongs to another category. That almost is what keeps the question alive. The scientific answer begins by narrowing the gap. Jupiter is not a star. It is not close to becoming a normal star under present conditions. To ignite long-term hydrogen fusion in the core, an object needs vastly more mass than Jupiter possesses. The threshold is not a small one. It lies far above the mass of any planet in the solar system. Even the dimmer class of objects called brown dwarfs, sometimes described as failed stars, are usually much more massive than Jupiter. These bodies can briefly fuse deuterium, a heavier form of hydrogen, if they are massive enough, and some can fuse lithium under the right conditions, but they do not sustain the full, stable hydrogen burning that defines a main sequence star like the Sun. Jupiter falls below even that lesser threshold. In that strict sense, it is not a failed star in the same way a brown dwarf is a failed star. It is simply a planet, though a very large one. And yet the question refuses to die because classification does not exhaust the mystery. Jupiter is not a brown dwarf, but it still forms in a region where the line between giant planet and substellar object grows blurry. In other planetary systems, astronomers find bodies several times the mass of Jupiter orbiting stars. Some are called super-Jupiters. Some edge toward the brown dwarf range. There is no clean emotional boundary separating one category from the next. The more mass an object gathers, the more it compresses itself. The more it compresses, the hotter its interior becomes, the more heat it traps, the more it resembles the faint beginning of a star. Jupiter already radiates more energy than it receives from the Sun, releasing leftover heat from its formation and slow contraction. It glows in its own subtle way, not with visible fire, not with fusion-driven brilliance, but with stored internal energy that has never fully escaped. It carries a trace of incompletion, as if some older process remains active inside it. That trace is enough to make Jupiter feel like a near miss, but the deeper reason lies in how stars and giant planets form. Both grow inside collapsing environments shaped by gravity, gas, and angular momentum. Both begin as accumulations inside disks or clouds. Both gather hydrogen and helium if conditions permit. The difference is not one of material alone. It is a difference of opportunity, timing, and control over mass. A star forms by collapsing directly out of a denser region of a molecular cloud. It gains access to a huge reservoir from the beginning. A giant planet like Jupiter forms within the disk around an already forming star. That is a weaker position. It is born downstream from the Sun, inside the Sun's own feeding zone. It must compete with the central object that is already taking almost everything. That imbalance is extreme. The Sun contains nearly all the mass in the solar system. Jupiter, despite its enormous size, holds only a tiny fraction by comparison. The ratio is so lopsided that the giant planet begins to look less like a rival to the Sun and more like a surviving remnant of what the Sun does not consume. In that sense, Jupiter does fail to become a star, but only in the same broad way that every planet fails. None of them begin in the place where starhood is likely. They do not condense independently from the cloud as separate stellar embryos. They emerge within the leftover disk after the main collapse has already chosen its champion. Jupiter is therefore not uniquely unlucky. It is simply the most massive of the bodies that are born too late and too far down the hierarchy of accretion. Still, the imagination lingers on the alternative. In many stellar nurseries, more than one star forms. Binary systems are common. Triple systems exist. Some stars are born with companions not because one planet nearly succeeds, but because the original collapsing cloud fragments into multiple dense centers early on. Each fragment becomes a protostar with its own access to mass. In such cases, the system is never truly single to begin with. The solar system may therefore owe its solitary sun not to the failure of Jupiter, but to the fact that the natal cloud does not fragment in the right way at the right time. A second sun would likely have required a second stellar core, not a more ambitious Jupiter. The difference matters. It means the solar system is not almost binary in the ordinary sense. It is fundamentally single from a very early stage. And yet there is room for unease in that conclusion, because the early history remains partly hidden. The Sun may have formed in a cluster of sibling stars. It may have experienced close encounters early on. Some models suggest that an additional massive planet may once have existed among the giants and later been ejected. Others imagine migration and resonance reshaping the outer system with surprising violence. If such rearrangements occur, then Jupiter's present state may not reveal how strange its youth truly is. A planet that now seems stable may once move through regions of the disk rich in gas, gathering mass at a dangerous pace before some process slows it. A slight change in disk lifetime, temperature structure, or migration history could produce a very different outcome. Jupiter does not need to become a star for its existence to feel contingent. It only needs to depend on thresholds that nearly tip another way. Modern models of giant planet formation tend to follow two main routes. In one, a solid core grows first through the accumulation of ice and rock beyond the snowline, the region in the disk cold enough for volatile substances to freeze. Once the core reaches sufficient mass, it rapidly draws in surrounding gas and swells into a giant. In the other route, a part of the disk becomes gravitationally unstable and collapses more directly into a massive gaseous body. The first mechanism is often favoured for Jupiter, though the details remain debated. Either way, time is critical. The gas disk does not last forever. Stellar radiation, winds, and internal processes gradually disperse it. A forming giant planet must gather enough gas before the reservoir vanishes. Jupiter succeeds spectacularly compared with the other planets, but even its success is incomplete. It becomes immense, then stops. The disk is exhausted or dispersed. Growth ends. A giant remains, but not a star. That stoppage is one of the most revealing moments in the whole solar system. It shows that cosmic formation is not simply about what gravity wants. Gravity always wants more. It pulls inward, gathers mass, deepens wells, and strengthens itself. But gravity acts inside environments with clocks. The disk cools. The sun brightens. Ultraviolet radiation strips gas away. Neighbouring stars in the birth cluster may erode the disk from the outside. Migration may move a growing planet into regions with less available material. Resonant interactions may alter feeding patterns. Jupiter's final mass is therefore not just a measure of what it can attract. It is a measure of what the environment allows before the opportunity closes. It does not become a star because the window shuts first. There is another reason Jupiter feels star-like even though it is not. Its influence on the rest of the solar system is enormous. It shapes asteroid populations, scatters comets, captures Trojans, perturbs resonances, and may help decide how much debris reaches the inner planets. In some eras, it acts like a shield, redirecting or intercepting bodies that might otherwise strike Earth. In other cases, it can send danger inward by disturbing distant objects onto new paths. It is not simply a passive giant sitting beyond the asteroid belt. It is one of the main gravitational authors of the solar system's later history. This makes its non-stellar status almost deceptive. Jupiter does not shine like a star, but it governs like one in the outer architecture of the system. And then there is the inward feeling Jupiter produces in human thought. A second sun is not merely an astronomical alternative, it is a different history for every world that follows. The habitable zone would shift, planetary climates would change, orbital stability could be altered, seasons, tides, and the long-term structure of the system might all look different. The question of whether Jupiter could have been a star is therefore not just about Jupiter. It is about how close the solar system ever comes to becoming another kind of place. The scientific answer says not very close in the strict mass required for fusion, but the emotional answer is harder to dismiss because Jupiter still sits near a conceptual border. It is large enough to suggest possibilities it cannot actually reach. That is why the mystery remains useful even after the physics is clear. Jupiter is not a star that fails at the last moment. It is a planet that reveals how formation depends on hierarchy, timing, and loss. The Sun takes the role of star so completely that everything else becomes secondary. Jupiter inherits grandeur without promotion. It grows huge, radiates internal heat, commands a system of moons, and still remains confined to the category of planet. In its scale, there is ambition. In its final state, there is restraint. It is the largest reminder that not all almosts in astronomy are true almosts. Some are illusions created by size and distance. But even illusions can point to real thresholds. Jupiter marks one of them. It shows how a world can come to seem like a failed sun, not because it nearly burns, but because it preserves, in silent mass and restless weather, the outline of a larger possibility that the solar system never actually allows. The edge of the solar system seems at first like a problem with an obvious answer. It should be where the planets end, or where Pluto wanders, or perhaps where sunlight becomes too weak to matter. Yet every simple boundary breaks down as soon as it is examined. The planets do not define the end because Neptune is not the last meaningful structure. Pluto does not define the end because Pluto is only one body among many in a wider outer region. Even the Kuiper belt does not define the end because objects exist beyond it, and because the Sun's influence extends far beyond anything visible in the ordinary planetary map. The solar system, once again, proves far less tidy than the image taught early on. Its order is real, but its borders are evasive. The farther outward the search moves, the less the word edge behaves like it should. This confusion becomes most visible through the Voyager spacecraft. Launched in the 1970s, Voyager 1 and Voyager 2 travel outward for decades. Long after their original planetary missions are completed, their cameras fall silent. Their power slowly declines as the plutonium in their radioisotope generators decays. Instruments are turned off one by one to conserve energy, even in old age. However, the spacecraft keep moving into regions no other mission has directly sampled. For years, they become symbols of departure. Many headlines announce that one or the other has left the solar system. The phrase is compelling because it sounds final, almost ceremonial, as though humanity has crossed some clean cosmic threshold. But the deeper truth is less simple and far more interesting. The voyagers enter interstellar space without necessarily leaving the solar system in the gravitational sense. They pass one frontier and reveal that it is only one of several. The frontier they cross is often described through the heliopause. To understand why that matters, the Sun must be seen not only as a source of light and gravity, but as a star that constantly releases a stream of charged particles known as the solar wind. This wind races outward in all directions, carrying the Sun's magnetic field with it, inflating a vast bubble in the surrounding interstellar medium. That bubble is called the heliosphere. Inside it, solar particles and magnetic effects dominate. Outside it, the gas, dust, and fields of the galaxy begin to assert themselves more strongly. The heliopause marks the boundary where the outward push of the solar wind is finally overcome by the pressure of the interstellar environment. It is not a wall. It is not a cliff. It is a transition region, irregular and changing. Where one influence yields to another, Voyager 1 is widely understood to cross this region in the early 20-teens, and Voyager 2 follows years later. Their measurements show abrupt changes in particle populations, magnetic behavior, and the surrounding plasma environment. The spacecraft do not suddenly enter emptiness. They enter another medium. The Sun's wind no longer rules there in the same way. In that limited but important sense, they pass into interstellar space, yet the phrase creates a subtle misunderstanding. Interstellar space is not necessarily outside the solar system if the solar system is defined by the full reach of the Sun's gravity. A spacecraft can leave the heliosphere while still remaining under the Sun's long gravitational influence. That distinction sounds technical until its implications settle in. It means the solar system has more than one edge, and the first edge encountered is not the final one. Even the heliosphere itself is stranger than early pictures suggest. It is often imagined as a smooth bubble, almost circular around the Sun, but measurements and models indicate something more distorted. The Sun is moving through the galaxy, orbiting the center of the Milky Way at tremendous speed, while also drifting relative to the surrounding local interstellar medium. That motion matters. As the solar wind expands outward, it meets the incoming pressure of interstellar material. The result is not a perfect sphere, but something more like a lopsided bubble with compressed and stretched regions. Some have compared it to the shape of a comet, with a blunter nose and a longer trailing region. Others argue for shapes more complex still, shaped by magnetic interactions that twist and channel the flow. The exact form remains debated because direct measurements are sparse and the scale is immense. What matters is that the Sun's domain is not symmetrical. Even its particle boundary bears the mark of motion through a larger environment. This alone introduces a deeper mystery. The solar system is often imagined as the dominant local structure, a self-contained system centered on the Sun. But the heliosphere reveals dependence. The Sun pushes outward, yet it is also being pressed upon. It carries its bubble through the galaxy like a ship moving through water, and the surrounding medium helps sculpt the very boundary that once seemed to belong only to the Sun. The solar system is not sealed. It is exposed. It travels through regions of differing density, temperature, and magnetic character, over long timescales. Those regions may change the size and shape of the heliosphere. Some researchers have even considered whether passage through denser interstellar clouds in the distant past could have compressed the Sun's protective bubble more severely, perhaps altering how much galactic cosmic radiation reaches the inner planets. That remains a subject of study and uncertainty, but the idea itself changes the tone of the story. The solar system does not merely occupy space, it moves through weather on a galactic scale. And yet, impressive as the heliosphere is, it still does not tell the whole story of belonging. A body can pass beyond the heliopause and still orbit the Sun if it has not gained enough speed to escape the Sun's gravity. This is the crucial shift from magnetic boundary to gravitational boundary. The heliosphere is defined by particles and pressure. The true outer reach of the solar system, in a more enduring dynamical sense, is defined by gravity. That makes it less visible and harder to picture. There is no glowing shell marking where solar gravity ends. There is only a gradual weakening of dominance, a region where the Sun still matters more than neighbouring stars for some objects, then matters less, then perhaps only barely. The shape of this region is often discussed through the idea of the Hill sphere, the volume around a body within which its gravity can retain dominance over smaller companions despite the pull of larger external masses. Applied to the Sun, this idea becomes vast and uncertain. The Sun sits among other stars, not in isolation. Alpha Centauri lies a little more than 4 light-years away. Barnard's star lies farther and is less massive. Other nearby stars contribute their own competing pulls, and the galaxy itself exerts a tidal influence across the region. This means the Sun's gravitational realm cannot be a neat sphere. It is stretched, squeezed, and weakened in different directions depending on the local stellar neighbourhood. In principle, its influence may extend several light-years, but stable long-term orbits near the outermost limits would be fragile. A distant icy body loosely circling the Sun could be nudged by passing stars, galactic tides, or molecular clouds. It might remain bound for millions of years, then drift away, or it might be sent inward after ages of near stillness. The true boundary becomes less like a fence and more like a fading jurisdiction. This has a strange emotional effect on the idea of exploration. The Voyagers, for all their triumph, are nowhere near the furthest likely members of the solar system if the distant comet reservoir exists as expected. They move through the heliosphere, then beyond it, but still remain deep inside the Sun's broader gravitational kingdom. The difference in scale is humbling. Voyager 1, travelling faster than any human-made object has ever permanently journeyed away from the Sun, would still need centuries just to approach the inner reaches of the hypothesized distant cloud of icy bodies, and far longer to move across it. The popular idea of escape begins to look almost theatrical. The spacecraft have left one environment, but not yet the family entirely. There is also something revealing in the fact that the first edge humanity touches is the one defined by wind rather than mass. It is easier to measure changes in plasma, particle counts, and magnetic fields than to identify the exact point where solar gravity ceases to dominate. In other words, the first true outward threshold available to observation is not the deepest one. The solar system presents its skin before its skeleton. It allows instruments to sense the fading breath of the Sun before they can meaningfully test the furthest reach of its hold. That sequence mirrors the broader theme that runs through its history. What appears obvious first is rarely fundamental. The neat edge is not the final edge. The first ending is only an outer atmosphere of influence, and once that is understood, the solar system becomes larger in a more unsettling way. Not larger in the simple sense of distance alone, but larger in conceptual depth. It contains zones defined by different laws of belonging. The interplanetary region is ruled by sunlight and major worlds. Far beyond that lies the realm of icy remnants and scattered objects. Beyond that lies the vast magnetic bubble of the Sun's wind. Beyond that may still lie bodies bound by gravity, drifting so far out that the Sun is only a bright star among stars, yet still not entirely released from its grasp. An object could be in interstellar space and still be, in a meaningful dynamical sense, part of the solar system. That paradox is not a trick of language. It is a genuine feature of reality. So the question of where the solar system ends turns out to reveal something more important than a distance. It reveals that the sun's influence comes in layers, and that those layers do not line up cleanly. Magnetic reach, radiative reach, planetary structure, icy populations, and gravitational dominance all fade at different scales. The solar system is not a single bordered entity. It is a nested hierarchy of diminishing control. The voyagers do not solve that puzzle by crossing the heliopause. They sharpen it. They show that one boundary is real, measurable, and historic, while also proving that it is not enough. The sun's breath ends there. Its grip does not. And in the space between those two facts, the old image of a small and neatly ringed system gives way to something broader and more elusive, a domain whose first edge can be crossed long before its true departure is even close. Gravity becomes harder to understand the farther outward the solar system is traced, because unlike light, rings, or planetary motion, it does not announce its boundary with anything visible. It fades without spectacle. Near the sun, its rule appears obvious. Planets orbit in steady paths. Comets swing inward and back out again. Spacecraft must fight the sun's pull with carefully measured speed and timing, but at great distances, the same force becomes difficult to separate from everything around it. Nearby stars begin to matter. The smooth orbit around the galactic center begins to matter. Passing clouds, distant stellar encounters, and the general tidal pull of the Milky Way begin to matter. The sun's gravity does not stop abruptly. It enters a region where possession becomes uncertain. That uncertainty is the real frontier. The idea often used to describe this region is the Hill sphere, the area around an object where its gravity remains stronger than the competing pull of something larger nearby. Around Earth, the Moon stays bound because it lies within Earth's gravitational domain despite the greater total power of the Sun. Around the Moon, a spacecraft can orbit because, close enough in, lunar gravity dominates over Earth's for that local motion. Scaled up to the Sun, the same principle becomes vast. The Sun also has a gravitational domain, a region within which objects can remain primarily bound to it rather than being claimed by neighbouring stars or the galaxy. But once the Sun is treated in this wider context, the image of a simple sphere quickly fails. The Sun does not float in emptiness. It sits inside a crowded and slowly shifting stellar neighbourhood. And that neighbourhood distorts everything. This is where the true edge of the solar system begins to lose the comfort of geometry. In textbook sketches, spheres are tidy. They're easy to imagine and easy to teach. In reality, the Sun's realm must be stretched more in some directions and compressed in others, because the surrounding stars are not evenly distributed. Alpha Centauri, the nearest stellar system, lies a little over 4 light-years away and contains more than one star. Its combined influence is not trivial. In that direction, the Sun's gravitational dominion is pressed inward more strongly than it would be in a quieter region. In another direction, the nearest significant competitor may be farther away or less massive, allowing the Sun's reach to extend more generously. Barnard's star, for instance, is smaller and more distant than Alpha Centauri. The asymmetry matters. It means the solar system's outer boundary is not merely invisible, it is irregular by nature. Even that is not the whole problem. The Hill sphere is a useful concept, but in the environment of the Sun it is only an approximation. The galaxy itself exerts a steady tidal field across large distances, gently pulling on loosely bound objects. As the solar system orbits the Milky Way, it passes through a changing stellar environment over immense spans of time. Stars drift by. Some pass close enough, on astronomical scales, to stir the outermost bodies. Molecular clouds may once in a great while pass near enough to alter the distant reservoir more deeply. The Sun's gravitational domain is therefore not a static possession. It breathes, distorts, and weakens under outside pressure. Objects near the limit may remain bound for ages, then be lost after a single unlucky encounter. Others may be almost free for millions of years, only to be nudged inward instead of outward. The boundary is not just asymmetrical, it is alive with slow vulnerability. That vulnerability gives the outer solar system a very different character from the planetary region. Inside the orbit of Neptune, even with all the complexity of resonances and perturbations, the Sun's authority is overwhelming. The planets are deeply bound. Their paths may shift over long timescales, but they are not on the verge of drifting off into interstellar darkness because of a passing star. Far outward, that confidence fades. A distant icy body taking perhaps hundreds of thousands or even millions of years to complete one orbit would move through a region where the Sun's hold is so weak that almost anything matters. A slight nudge from galactic tides, a distant stellar passage, a redistribution of mass within the system. These can be enough to alter the path profoundly. Stability there is not the same as stability here. It is provisional, statistical, easily disturbed. This is why astronomers often treat the furthest likely long-term frontier of the solar system more cautiously than the maximum theoretical reach of the Sun's gravity. In principle, the Sun may influence objects out to distances of a few light years in certain directions. In practice, truly stable. Long-lived orbits are expected to survive only well inside that furthest mathematical reach, beyond roughly a light year, perhaps somewhat more or less depending on direction and conditions. The environment becomes increasingly treacherous for any object trying to remain a faithful satellite of the Sun over billions of years. The solar system may therefore possess not one gravitational edge but several meaningful thresholds. There is the maximum realm where the Sun can dominate at all. There is the more conservative realm where stable populations can endure. And there are transitional zones between them where bodies are not fully secure yet not fully lost. This layered uncertainty begins to reshape the meaning of belonging. Near the Sun, belonging is easy to define. Earth belongs to the solar system with no ambiguity. Jupiter belongs. Even the scattered dwarf planets beyond Neptune belong, however eccentric their paths may be. But what of an icy body so distant that the Sun appears only as one bright star among many, yet still exerts the strongest pull over the long arc of the orbit? What of an object that remains bound for hundreds of millions of years, then escapes after a stellar encounter? What of one that spends most of its time so far away that the difference between membership and exile is a question of minute perturbations accumulated over ages? At that distance, belonging becomes a matter of history as much as present dynamics. The object belongs until something edits the record. There is a strange emotional consequence to this. The solar system, usually imagined as a clearly enclosed family, turns out to have an outer region more like a faded citizenship than a firm border. The Sun can claim bodies it can barely hold. It can influence things too distant to warm, too remote to illuminate strongly, too weakly bound to trust forever. These are not planets. They are not worlds in the ordinary narrative sense. Many may be dark, frozen remnants of the system's violent beginning, exiled to the frontier by the migrations of giant planets and the early chaos of close encounters. Yet they may collectively define the true breadth of the solar system better than the planets do. Precisely because they occupy the zone where the Sun's rule is most tested. In that sense, gravity preserves memory differently from the disk that shapes the planets. The disk remembers one early spin and leaves a shared plane. Gravity remembers every scattering event. It remembers giant planets hurling icy bodies outward. It remembers passing stars trimming the outer reservoir. It remembers galactic tides lifting some orbits and suppressing others. The far frontier is therefore not a simple leftover. It is an archive of disturbances. Bodies pushed there during the youth of the solar system can remain for immense ages, carrying traces of a time when the giant planets likely moved. Resonances shifted, and countless smaller objects were flung into darkness rather than allowed to remain near the sun. The inner system contains the finished worlds. The outermost gravitational domain contains the evidence of how costly that finishing process is. This is one reason the unseen outskirts matter so much scientifically. They may preserve clues to the early architecture of the solar system that the inner planets no longer show plainly. Ancient icy bodies, stored in extreme cold and darkness, may retain chemical and dynamical information from the era of formation. Their distribution, if it could ever be mapped well enough, might reveal how Jupiter and Saturn migrate, how Neptune shifts outward, how efficiently planetesimals are scattered, and how often the Sun's natal cluster perturbs the system in its first few million years. The problem is that most of this frontier is inferred rather than observed directly. The Sun's invisible kingdom is too large and too dark for easy survey. Much of what is believed about its distant population comes not from seeing the bodies themselves, but from seeing what sometimes returns from that darkness. That return is one of the most intriguing features of the whole region. A distant object near the edge of solar rule is not merely threatened with loss, it is also poised for redirection. A slight push the wrong way can free it forever. A slight push another way can send it falling sunward on an orbit so elongated that it becomes a rare comet entering the inner system after an absence longer than human civilization. In that sense, the outer boundary is not just a border, it is a reservoir of delayed arrivals. The most distant members of the solar system may spend almost all of their existence unseen and inert, then appear suddenly as bright comets, streaking through the inner regions as if they have come from nowhere. But they do not come from nowhere. They come from the zone where solar belonging is weakest and therefore most easily disturbed. This gives the Sun's outer gravity an almost paradoxical role. It is at its least powerful where it becomes most narratively important. Near the planets, gravity holds everything securely and reveals little drama except through impact and resonance. At the frontier, where the Sun's grip is frail, the system becomes permeable. Things can leave, things can return. Ancient debris can be preserved, then awakened. The edge becomes not a stopping point, but a region of exchange between system and galaxy. The solar system is not enclosed there, it is negotiable, and that may be the most accurate way to understand the invisible kingdom of gravity. It is not a neat sphere, not a final shell, not a place where the Sun's power either exists or does not. It is a weakening field full of fragile loyalties. Some objects remain bound because nothing has yet persuaded them otherwise. Some are lost because a distant star passes by at the wrong moment in deep time. Some are thrown inward and become visible only because the boundary is unstable. The real outer solar system is therefore not simply large. It is uncertain in a profound way. It stretches beyond the magnetic bubble, beyond the familiar planets, beyond the last ordinary maps, into a region where being part of the Sun's domain is less a permanent condition than an ongoing negotiation with the rest of the galaxy. Beyond Pluto, the solar system stops behaving like a place built for intuition. Distances increase so sharply, sunlight weakens so severely, and the bodies become so small and so widely scattered that the old image of a compact planetary family finally begins to collapse. The outer planets still feel like part of the same grand arrangement. Jupiter, Saturn, Uranus, and Neptune are immense enough to dominate imagination. Even Pluto, though diminished in status, remains familiar because it carries a name, a tilted orbit, and a long cultural afterlife. But farther out, the narrative thins into darkness. There is no single last world waiting at the rim. There is no clean line after which nothing remains. There is instead a gradual transition into regions made mostly of leftovers, fragments, dormant nuclei, and populations inferred more often from their effects than from direct sight. This is the realm beyond the neat map, where the solar system becomes less a set of worlds and more a field of suspicions. The first of these regions is the Kuiper Belt, a broad zone beyond Neptune populated by icy bodies, dwarf planets, and debris left over from the era of planetary construction. Even this description is only a beginning, because the Kuiper Belt is not one tidy ring. It contains families of objects with different orbital histories. Some are relatively stable and remain in resonant patterns with Neptune. Some occupy more classical belt-like orbits. Some are scattered into paths so elongated that they barely seem to belong to a belt at all. Pluto is one member of this wider population, not its ruler and not its edge. Make, Haumea, Eris, and many smaller bodies add to the picture, revealing that the outer solar system contains a hidden population of frozen remnants far more varied than the old 9-planet model ever suggests. What makes this region so revealing is that it does not look like a finished product. The inner solar system gives the impression that major building is over. The planets are large, differentiated, settled into long-term identity. The Kuiper Belt does not offer the same sense of completion. It looks more like a storage zone of interrupted outcomes. Some bodies are large enough to become round under their own gravity. Others remain irregular. Some may be ancient survivors from the original planetesimal population. Others may be fragments produced by collisions. Haumea, with its rapid spin, elongated shape, and family of related fragments, is one of the clearest hints that the outer dark is not motionless history, but the aftermath of specific violence. Even in the cold, impacts still matter. A world can be broken there and leave a signature that endures for ages. This matters because it suggests that the outer solar system is not merely where things failed to become planets. It is where the record of competition remains legible. The giant planets, especially Neptune, likely shape much of what is seen there. Resonances trap some objects into stable timing patterns. Migration in the early solar system may push bodies outward, scatter them, and repopulate distant zones. Some models propose that Neptune does not form exactly where it now orbits, but moves outward through a disk of icy planetesimals, throwing some inward, some outward, and some into resonant lockstep. If that is true, then the Kuiper Belt is not a passive belt of leftovers. It is a sculpted field, a region whose current structure contains the memory of planetary motion long after the migration itself ends. Bodies drifting in darkness still mark the passage of worlds much larger than themselves. Yet even the Kuiper Belt is not the true deep frontier. It is only the beginning of outward obscurity. Far beyond it lies the most elusive region in the solar system's accepted architecture, the Oort cloud. Unlike the planets, unlike the major moons, unlike even the Kuiper Belt, this immense population has not been directly observed as a complete structure. No spacecraft has crossed it. No telescope has photographed it as a resolved cloud of countless distant bodies around the Sun. Its existence is inferred, and inferred strongly, from the behavior of long-period comets. These comets arrive on orbits so vast and elongated that they cannot easily be explained as ordinary members of the planetary region or even of the Kuiper Belt alone. They seem to come from a distant reservoir, a sphere or thick shell of icy objects surrounding the solar system on a scale far beyond the planets. The Oort cloud is therefore one of the largest recognized structures in the solar system, and one of the least directly seen. That combination gives it unusual power over the imagination. It is not fictional. It is a serious scientific construct, supported by decades of cometary dynamics, and the need for some reservoir that can feed the rare visitors arriving from extreme distances. But because it remains mostly unseen, it retains a peculiar openness. Its size is estimated rather than mapped. Its density is sparse. Its total population may reach into the billions or trillions of icy bodies, yet each object may be separated from the next by vast emptiness. It is not a cloud in the familiar sense, not a mist one could drift through and see crowded around. It is more like an enormous volume of darkness in which frozen remnants orbit so slowly and so distantly that the sun's warmth barely matters at all. The name suggests softness. The reality, if it exist broadly as described, would be more austere than almost anything else in the solar system. The distances involved resist instinct. Voyager 1, moving outward faster than any earlier spacecraft sent permanently away from the Sun, would still take centuries merely to approach the innermost expected reaches of this cloud, and vastly longer to pass across it. That fact alone changes the scale of the solar system from large to almost abstract. The planetary system that seems expansive in diagrams becomes, in this context, a compact bright centre surrounded by a wilderness that stretches for a significant fraction of the distance to the nearest stars. The Oort cloud, if fully counted as part of the solar system, means the Sun's family does not end in a planetary choir. It ends in a near-invisible diaspora of frozen bodies scattered across an enormous gravitational twilight. And yet the Oort cloud may be one of the most important regions for understanding how the solar system forms and survives. It is thought to originate not from local quiet assembly, but from rejection. Icy planetesimals forming among the giant planets are scattered outward by repeated gravitational encounters. Some are ejected entirely into interstellar space. Others lose just enough energy in the wider galactic environment, or experience the right pattern of perturbation from nearby stars and tides to remain loosely bound on giant orbits. Over time, these scattered bodies populate the distant cloud. If that picture is correct, then the Oort cloud is made of exiles. It is not the outer continuation of the disk in the ordinary sense. It is a cemetery of near losses, a sphere assembled from bodies that the giant planets fling away but fail to erase completely. This gives the region a haunting character. The most remote members of the solar system may not be the noble survivors of primordial calm. They may be the displaced casualties of planetary formation, objects pushed so far out that they spend millions of years in darkness between brief turns around a sun that, from their perspective, scarcely dominates the sky. Some may never return inward again. Others may be nudged by passing stars or by the tidal pull of the Milky Way until their orbits change just enough to send them falling toward the inner system. When that happens, a comet appears. It brightens as ices sublimate near the sun, forming coma and tails, and for a brief interval a body from the furthest cold is transformed into one of the most spectacular sights in the sky. Then it leaves again, sometimes forever, sometimes to return after an interval longer than recorded history. In that sense, long-period comets are not just visitors. They are messages from the least accessible part of the solar system. Their chemistry can preserve ancient volatiles. Their orbits can hint at the structure of the distant reservoir. Their arrival rate can be altered by galactic tides, stellar passages, and even the sun's motion through the Milky Way. The Oort cloud, though unseen in its full extent, interacts with the inner solar system through these rare emissaries. What is hidden does not remain silent. It sends fragments inward when the outer balance is disturbed. This raises another possibility, one that remains partly speculative but difficult to ignore. If the outermost cloud is so sensitive to outside influence, then the solar system's deep past may be written there not only in bodies cast out by the giant planets, but also in the marks of the sun's birth environment. The young sun may form in a cluster of sibling stars. If so, close passages early on could help shape the outer cloud, lift the perihelia of extreme objects, and trim the edge of the sun's distant population. Some astronomers have looked at unusually detached bodies in the far outer system, such as Sedna, and seen hints that ordinary scattering by the known giant planets may not fully explain everything. Sedna's orbit is too distant and too detached from Neptune to fit comfortably into the simplest story. It may point to ancient stellar encounters. It may hint at unseen influences in the early solar system. It may simply mark a more complex history of migration and scattering than once assumed. Whatever the final explanation, it serves as a reminder that the dark beyond Pluto is not empty enough to be simple. For a time, speculation about a hidden distant planet gains attention, partly because of these strange outer orbits. A hypothetical planet far beyond Neptune is proposed as one way to account for certain clustering patterns among extreme trans-Neptunian objects. The idea remains unconfirmed and debated. Observational bias complicates the pattern. Alternative explanations persist. No direct detection settles the matter. Yet the very plausibility of the idea says something important about the region itself. The outer solar system is so poorly mapped, so vast, and so observationally difficult that even a large unseen body remains a live possibility for serious discussion. That is not because astronomy has failed. It is because the territory is genuinely hard. The darkness beyond Pluto is not just remote, it is structurally hidden from easy certainty. And this returns the story to its quietest mystery. The solar system seems most knowable where it is brightest and most incomplete where it is largest. Its planets are iconic, named, photographed, and visited. Its true outer domain is mostly inferred, calculated, and glimpsed through rare intrusions. The Kuiper belt shows a frontier of surviving fragments. The Oort cloud suggests an even vaster halo of exiled ice. Between them lies not a final edge, but a widening uncertainty. Pluto does not stand at the rim of a finished system. It stands near the beginning of the dark. Beyond it, the solar system becomes a place where objects are counted by prediction, where maps are drawn from returning comets, and where the most distant members may spend their entire existence almost untouched by sunlight. In that far realm, the sun still rules, but only faintly, and the bodies that remain loyal to it do so from such immense distances that they seem less like neighbours than like memories the solar system has nearly forgotten. Scale is where the solar system most easily defeats understanding, because the mind keeps trying to turn distance into something intimate and fails every time. A diagram on a page encourages the illusion that planets are neighbours arranged in a tidy sequence, each one separated by a manageable gap, even when the distances are written down. The imagination quietly compresses them. Mercury feels close to the Sun. Earth feels comfortably placed. Jupiter seems far. Neptune remote. Pluto almost at the edge. But this sense of spacing is shaped by images that cannot afford honesty. If the planets were drawn to scale in size and distance on the same ordinary page, most of the page would contain almost nothing at all. The solar system is not primarily made of worlds. It is made of emptiness, and that emptiness is so dominant that the worlds can look almost accidental within it. That is why scale models are so revealing. They do not solve the problem, but they expose it. If the sun is reduced to the size of a football, the inner planets shrink to tiny points, and the first meaningful distances already push them far away across open ground. Mercury becomes a speck at a distance that feels excessive for something supposed to be the sun's closest companion. Venus follows. Earth takes its place a little farther out, the familiar world suddenly no larger than a bead. Mars recedes again. Then, after what already feels like enough empty space, the asteroid belt begins. The gap between Mars and Jupiter is not decorative. It is a real widening, a silence in the layout that reminds the observer that even before the giant planets begin, the solar system is already defined by intervals rather than by objects. Jupiter then arrives not only as the largest planet, but as the first body distant enough to shift the emotional scale of the system. It is several times farther from the Sun than Earth, Saturn more distant still. Uranus and Neptune continue the outward spread until each step becomes a lesson in thinness. The bodies are large by planetary standards, but tiny relative to their separation. By the time Neptune is placed in such a model, the Sun no longer feels like a centre of clustered worlds. It feels isolated, surrounded by a few remote companions and an enormous amount of nothing. Pluto, even when included for perspective, does not close the pattern. It only shows how far the arrangement can stretch before the darkness truly begins. A smaller scale makes the lesson harsher. If the Sun is reduced to a grain 1 millimeter across, then Mercury sits only a few centimeters away, Venus a little farther, Earth about 10 centimeters from the tiny false Sun, Mars beyond that, Jupiter more than half a meter away, Saturn just over a meter, Uranus more than 2 meters, Neptune more than 3. Pluto, when included, lies beyond 4 meters from a Sun barely visible as a speck. On a tabletop or across a room, the planetary region suddenly feels sparse and oddly fragile. The giant worlds, so imposing in astronomy, are reduced to dust like signs spaced across a mostly empty strip, and yet even this model, for all its power, still conceals the deeper shock because it ends where the instinct wants the solar system to end. It reaches the planets, perhaps the Kuiper belt, then stops before the emptiness becomes truly difficult. The real emotional rupture comes when the nearest star is added in the same 1 millimeter scale. Alpha Centauri does not appear a few steps away, or down the road, or even across a city. It appears roughly 30 kilometers distant. That one figure does more than communicate distance. It breaks the false intimacy of the night sky. The stars seem densely sprinkled above Earth because vision flattens them into one dome. But in physical space, even the nearest stellar neighbour lies so far from the Sun that all the planetary spacing inside the solar system begins to look local, almost cramped by comparison. The gap from the Sun to Pluto, so striking within the planetary system, becomes nearly meaningless against the gap from the Sun to the next star. A small room can hold the planets in such a model. Reaching Alpha Centauri requires a journey across an entire city and beyond. This is where emptiness stops being a simple fact and starts becoming a mystery of structure. Why is matter arranged this way at all? Why do stars sit so far apart relative to their size? Why are planetary systems tiny islands in such wide separation? Part of the answer comes from how star formation works. Molecular clouds are large and diffuse. Dense cores collapse into stars only in limited regions. Much of the original material is dispersed or consumed, and the final stars that emerge are separated by enormous distances because gravity gathers matter into local centers rather than into a continuous field of luminous objects. But even with that explanation, the result remains difficult to absorb. The solar system is not just large, it is locally large and cosmically lonely. That loneliness changes how the neighborhood is imagined. Alpha Centauri is the nearest known stellar system, yet even its closeness is deceptive. It contains more than one star, and Proxima, the faint red dwarf loosely associated with the brighter pair, orbits at a great distance from them. The nearest neighbour is therefore not one simple sun standing beside this one. It is another layered system, itself internally separated, itself occupying a gravitational domain that does not touch the sun's except at the farthest, weakest margins. Between them lies no chain of planets, no broad cloud of warm gas, no hidden bridge of worlds. There is interstellar space, thin, cold, and immense. The nearest star is near only in a relative sense. In human scale, it is still unreachable by any ordinary standard. And yet the solar system does not feel isolated when viewed from inside because the sun dominates perception so completely. Daylight hides the stars. The planets move through the same sky. The moon provides a constant nearby companion. Even deep space missions still remain under solar influence. It is possible to spend a lifetime thinking of the solar system as a full environment because local brightness disguises external distance. Only when the system is shrunk into a model does the broader reality emerge. The worlds are not packed. The stars are not adjacent. The galaxy is not crowded in the way the eye suggests. It is structured by vast intervals in which almost nothing visible happens for extraordinary distances. This changes the meaning of travel as well. Voyager, New Horizons, and every other outward mission seem bold because they cross planetary distances, and they are bold. But scale reveals that these are motions within one local courtyard, not steps across the stellar neighbourhood, even travelling faster than any earlier mission escaping the Sun. A spacecraft would need thousands of years to reach the nearest stars with current technology. The difference between moving across the solar system and moving between stars is not merely quantitative, it is almost a change of category. The first is exploration within a family. The second is passage across an ocean so empty that even the family itself shrinks to a point behind the traveller, long before another sun begins to feel truly near. This immense spacing also affects how the solar system's origin is understood. If the Sun forms in a birth cluster, as many stars do, then its earliest neighbours may once have been much closer than the modern stellar neighbourhood suggests. Close encounters in that youth could have shaped the distant outer system, lifted the orbits of detached bodies, and helped sculpt the Oort cloud. Over time, the cluster disperses, and the Sun becomes part of a looser galactic pattern where the nearest stars are measured in light years. The loneliness seen now may therefore be deceptive in another way. The solar system could begin in relative company and only later drift into this wider spacing. That possibility adds a subtle tension to the stillness of the present. The emptiness around the Sun may not be how things always are. It may be what remains after an earlier crowd thins out. There is also a more unsettling lesson in the scale model of the solar system. It reveals how little of the system is actually made of places. Human imagination prefers destinations. Mercury is a place. Mars is a place. Europa, Titan, Pluto, and perhaps distant dwarf planets can all become places in the mind because they have surfaces or identities or weather or geology. But once the distances are honestly laid out, destinations begin to feel secondary. The dominant reality is transit. Space is something crossed much more than something occupied. The planets are rare interruptions in a mostly empty architecture. This does not make them less important. It makes them more improbable. In such a sparse design, every world seems like a local concentration against overwhelming dilution. The solar system starts to resemble not a machine built from parts, but a scattering of dense exceptions held inside a much larger void, and that, in turn, deepens the question of how habitability ever arises. Earth is not merely one planet among many. It is a narrow condition achieved in an environment where most locations are either too hot, too cold, too airless, too violent, or too remote from energy sources. The scale model makes this plain. The habitable zone, even around a sun like this one, is not a broad kingdom. It is a relatively thin band compared with the total volume of the system. A slight inward shift leads toward worlds like Venus. A slight outward shift moves toward colder and harsher conditions. The vastness of the solar system does not imply a vast abundance of living worlds. It may instead imply that life occupies a very small fraction of the available stage. The nearest star sharpens that thought rather than easing it. If Alpha Centauri is 30 kilometers away in the 1 mm model, then any Earth-like world around it would be part of another local miracle across an enormous gap. The galaxy may hold countless such worlds, but scale ensures that each one is surrounded by profound separation. The night sky looks crowded with stars, yet the physics beneath that view suggests that even when life-friendly conditions arise, they do so in isolated pockets divided by empty distances that challenge contact, travel, and certainty. The nearest possible other home, if it exists at all, is still unimaginably far when measured against the dimensions of one world, one species, one lifetime. So the purpose of scale is not only to amaze, it is to correct a persistent falsehood. The solar system is not a compact arrangement of nearby objects. It is a bright central star surrounded by a few major worlds, many minor bodies, and an overwhelming abundance of open space. Beyond that lies a still greater gulf before the next stellar domain begins. Every honest model reveals the same thing. Planets are rarer in space than the sky suggests. Stars are farther apart than the eye implies. The local neighborhood is not intimate. It is stretched thin across distances so extreme that even the nearest neighbor feels more like a distant rumor than a companion. The solar system, when scaled truthfully, does not become smaller and easier to grasp. It becomes stranger. It turns into an island whose coastline is already vast and whose nearest shore lies so far away that the sea between them begins to feel like the main feature of reality itself. The most persistent misconceptions about the solar system survive because each one begins with something that seems reasonable. The sun looks like fire, so it is treated as a burning ball. Mercury lies closest to the sun, so it is assumed to be the hottest planet. Pluto feels remote enough to be imagined as the final outpost. Asteroids seem dangerous in films, so the asteroid belt is pictured as a crowded hazard of tumbling rock. Comets arrive with glowing tails, so it is easy to believe they always possess them. These are not foolish errors. They are the natural byproducts of looking at a system whose true logic is hidden beneath appearance. And once those first assumptions begin to fail, a more unsettling pattern emerges. The solar system is not wrong in one or two familiar ways. It is almost designed to invite false certainty. Take the sun first, because nearly every other misunderstanding begins there. It glows with such ferocity that ordinary language reaches at once for fire. But fire, in the usual sense, is chemistry. It feeds on oxygen and fuel. It rearranges molecules. The sun does nothing so modest. Its light is born from nuclear fusion deep in the core, where hydrogen nuclei are pressed together under enormous temperature and pressure until they become helium, releasing energy that takes immense spans of time to work its way outward. By the time that energy escapes from the visible surface, the surface itself is still hot enough to shine brilliantly. Yet what is being witnessed is not burning in the everyday sense. It is a star using the force that powers stars. That correction sounds simple, but it opens something larger. The solar system is anchored by a process far stranger than the language learned early in life is prepared to describe. The central object is already beyond instinct. The same thing happens with planetary heat. Mercury appears closest to the sun and therefore seems destined to be the hottest world. Yet Venus, farther out, holds that title because its dense atmosphere traps heat in a runaway greenhouse effect so effective that its surface becomes hotter on average than Mercury's. Here the misconception is corrected by atmosphere, by the invisible envelope rather than by raw distance. That matters because it overturns one of the most primitive expectations in astronomy. Nearer does not always mean hotter. The character of a planet matters as much as its place. This turns the solar system from a simple temperature gradient into something more contingent. A planet is not merely assigned a fate by distance. It negotiates with sunlight through chemistry, pressure, cloud, circulation, and history. Venus is not just warm because it is near the sun. It is infernal because it keeps heat with almost vindictive efficiency. That distinction deepens the mystery of Earth as well. If one nearby world becomes a furnace and another remains habitable, then location alone never tells the whole story. Mercury itself carries another correction. For a long time it is imagined to keep one face permanently turned toward the sun, tidally locked the way the moon keeps one face toward Earth. The idea seems to fit its closeness and its slow rotation, yet radar studies reveal something subtler. Mercury rotates 3 times for every 2 orbits around the sun. It is caught in a resonance, not a full lock. This is a beautiful example of how the solar system often chooses the stranger option between 2 simple ones. Worlds are rarely content to fit the first intuitive pattern. They settle into resonances, spin-orbit couplings, and long-term behaviors that look almost designed to resist easy summary. Mercury is not just a scorched inner world. It is a demonstration that even one of the most accessible planets can hide a rhythm no unaided eye would ever guess. Then there is Saturn, perhaps the planet most associated with uniqueness. Its rings are so grand in the human imagination that they seem like a defining privilege. Yet the other giant planets also possess rings, though far fainter and harder to see. Jupiter has them. Uranus has them. Neptune has them. The misconception here comes not from total error, but from contrast. Saturn's rings are so spectacular that they drown out the quieter truth. Once the correction is made, the solar system becomes more unified and more mysterious at once. Ring systems are not a singular wonder. They are a recurring feature around giant planets, suggesting that debris, tides, and orbital confinement form a repeated pattern rather than one exceptional display. The question then is no longer why Saturn alone has rings, but why Saturn's rings are so vivid compared with the others, and whether that brilliance marks a special youth, a special history, or only a special moment in a structure that may not last forever. The asteroid belt is another place where appearance and reality diverge sharply. Films teach closeness, urgency, collision. The actual belt, stretching between Mars and Jupiter, is sparse on the scale of travel. Spacecraft cross it without weaving through walls of rock. Most asteroids are separated by enormous distances. The total mass of the entire belt is small compared with a true planet. That correction could make the belt sound less interesting, but it does the opposite. It reveals the belt not as a failed swarm packed with danger, but as the thinned remains of something that never becomes a world. Probably because Jupiter's gravity stirs the region too strongly for accretion to complete its work. The mystery deepens once the drama is removed. The asteroid belt is not exciting because it is crowded, it is exciting because it is incomplete. It is a place where planetary formation stalls, where an expected world never quite arrives. Comets suffer a similar misunderstanding. They're imagined as permanent objects with bright tails trailing behind them through the darkness. In reality, far from the sun, a comet can be quiet, cold, and visually unremarkable, more like a dark nucleus than a celestial banner. The coma and tail appear when solar heating wakes the frozen surface, releasing gas and dust. Even then, the tail does not trail behind in the ordinary sense. It points away from the sun, shaped by solar radiation and the solar wind. Once again, the correction removes the easy image and replaces it with something more subtle. A comet is not always spectacular. It becomes spectacular under specific conditions, briefly transforming from a cold relic into a luminous event. The solar system is full of objects like that. Bodies whose true nature is hidden until the right environment exposes it. Pluto perhaps carries the emotional, weightiest correction of all. Many still think of it as the last planet, the final marker of the solar system's edge. Yet Pluto is only one member of a larger outer population. It is not alone, and it is not the boundary. Beyond it lie other dwarf planets, scattered bodies, detached objects, and the far more distant reservoirs discussed only indirectly through cometary behaviour. This is more than a taxonomic adjustment. It is a structural revelation. The solar system does not end with a named little world. It fades into populations, then into inferred populations, then into weakly bound darkness. Pluto's demotion becomes symbolically important not because it loses dignity, but because it loses the role of final signpost. The old map ends there. The real one does not. Even the age of the solar system is misunderstood when folded too casually into the age of the universe. The solar system is not born with the Big Bang. It arrives much later, after stars live and die, after heavier elements are forged, after galaxies have already matured enough to seed molecular clouds with the ingredients of planets and life. This correction gives the solar system a historical position rather than a mythic one. It is not primal. It is late enough to inherit the rocks of Earth, the iron in planetary cores, the carbon in living things, and the radioactive clues in meteorites all point toward earlier stellar generations. The solar system is young compared with the universe, but enriched by what comes before it. That means its story is never only local. Even its material composition carries the memory of ancient stellar deaths. The sun lights a system assembled from previous endings. One misconception underneath many others is that the solar system is finished. The planets are formed, the main architecture is set, so the system feels complete. Yet signs of incompletion appear everywhere. Near Earth objects continue to cross planetary paths. Saturn's rings may be temporary on long timescales. Moons with subsurface oceans remain geologically active. Comets still enter from deep reservoirs. Asteroids still collide. The sun itself evolves, brightening gradually over immense spans. Even orbital stability, though robust in the near term, is not absolute forever. The solar system is settled enough for human history to unfold inside it, but not settled in any final cosmic sense. It is still changing, only more slowly than instinct prefers to notice. This is where the last and perhaps deepest misconception reveals itself. The solar system is often imagined as a solved structure because its major members are named and measured, but naming is not the same as understanding. The outer reservoirs remain partly hidden. The early migration of the giant planets is reconstructed rather than watched. The exact origin of unusual bodies on extreme orbits is debated. The detailed chemistry of formation, the timing of impacts, the evolution of atmospheres, the persistence of hidden oceans, and the true long-term future of rings and moons remain active questions. Even seemingly simple facts, such as where the solar system truly ends, unfold into layers of magnetic boundaries, gravitational boundaries, and loosely bound transition zones. The better it is known, the less the system resembles a finished textbook diagram, and the more it resembles a deep archive with missing pages. That is why every corrected misconception expands rather than shrinks the wonder. The sun is not ordinary fire, which makes it stranger. Mercury is not simply the hottest world, which makes planetary climates more complex. Saturn is not uniquely ringed, which makes ring formation more universal and more puzzling. Pluto is not the edge, which makes the solar system larger and darker than the old image allows. Comets are not always luminous, which makes their awakenings more dramatic. Asteroids are not densely packed, which turns the belt into a story of interrupted formation rather than constant collision. The corrections do not domesticate the solar system. They remove easy myths and expose deeper structures. And after all of those adjustments, one final uncertainty remains in the background. Perhaps the greatest misconception of all is that the solar system is mainly a collection of objects. In truth, it may be more accurate to see it as a collection of processes that have not fully ended. Collapse leaves a disk. The disk leaves planets. Collisions leave moons and scars. Scattering leaves distant reservoirs. Heat leaves weather. Tides leave fractures. Gravity leaves resonances. The visible worlds are only the current expression of older motions still working themselves out. The solar system is not merely what exists around the sun, it is what continues to happen there, slowly, quietly, and often beyond direct view. The more closely it is examined, the less it feels like a completed arrangement, and the more it begins to resemble an unfinished conversation between order and disturbance, memory and change, light and the dark that still waits beyond the last familiar name.